a new era of generative image models may have formed. Well, I say new. It's kind of new. It uses an autoregressive technique, but the idea of how they do that is quite different from other generational methods. Somebody recommended me this paper, and I'm very glad they did. This is a very, very good paper. So let's get into how they model this. This is called VAM. Yeah, I think it's VAM or VAR, video or visual autoregressive modeling. Yeah, VAR right here. And the idea is to instead produce a image using an autoregressive method as opposed to a image-to-image method, a bidirectional method. So usually what you do is, or I guess nowadays we use a diffusion model, and you used to use convolutions, but in the past, I don't know, months, we've seen DiTs be significantly better in every way than convolutions, because everyone loves transformers. Attention, it's all you need. So for a image to generate it, what you usually do is well, I'm not gonna go through the whole diffusion process because this video isn't going to be about diffusion. If you're curious, there's like a billion videos on diffusion, but this is a different technique. So what you usually do to generate to generate an image is you would take this image, so whatever this image may be. There we go, normal cat. Split up the image into a bunch of patches. So this patch would go here, this patch would go here, this patch would go here, and you're going to flatten the patches. So this patch here, this first part would turn into this part here, this second part would turn to this part, and so on. So you just take the pixels, you flatten them into so-called tokens. So you're tokenizing the image into 9 parts. And this tokenization allows you to throw it through a transformer. So you end up with this sequence, which is, say, S by D, where D is your dimensionality, which is the dimension of each of these patches, and S is the number of patches you have. I guess I can do P. So something like that. You then send this through a transformer, and it outputs something. It'll just be image to image, so you give it an image, it outputs an image. In the case of diffusion models, this would be your image X, your noisy image, so maybe X plus some noise, and this here would be the predicted noise. And this whole prediction happens at once, and this is diffusion transformers. You then remove the noise, and you do this over and over and over again. So you'd send it through again, so you send it through once, you remove the noise, you then send it through again, remove some more noise, and send it through again, remove some more noise, over and over again until you complete the diffusion process. So that's a brief overview of diffusion transformers, but notice that this is image to image. So we send this image through, and we get out the entire image and noise at every pixel. So this is what's usually done. Now, if we try to, this is a really good way of doing it. The problem is the inference time it takes forever to do inference on this, because you have to do a ton of forward passes with this massive image. And you can reduce that by using latent diffusion, but it still requires quite a lot of time. And this is one of the problems that they address. The amount of time it takes to generate an image using diffusion is a very, very long time, even with all the reduction techniques we have nowadays. Now, if you wanted to make this an autoregressive method, you could just take this. I'll use the same. Yeah, let me take this, move it down. So, come here. There. So if we wanted to make this autoregressive, we could do so by taking the patches that were generated by this, or taking the patches of the image, and do normal autoregressive training. So we pass this through the transformer for all tokens. And the idea is to allow say, this token here to generate this next part here. So this upper left part of the patch, or this upper left patch would generate maybe this patch here. And then these 2 patches would generate this patch here. So these 2 patches would generate this patch, and then these 3 patches would generate this patch, and so on. So if we only had this part of the sequence right here, this patch will hopefully somehow predict this patch here, which would be this top right patch. But intuitively, this feels a bit off, and intuitively, you would be right that this is quite a weird way to model an image. An autoregressive technique like this doesn't really make any sense. It makes a lot of sense with text because there is a obvious one-dimensional. There's an obvious one-dimensional autoregressive path. If you have the cat does not like sitting on mats, then there's an obvious direction. You generate this token, and the word cat obviously has a correlation with, like, there's an obvious, or I guess maybe not cat, but maybe the word does has some correlation with the word the in cat and can be generated from that. However, this top right of the image does not necessarily have that. It's not as obvious. There's obvious one-directional correlation, or there's obvious one-directional causality. There is not obvious one-directional causality here. Nothing says that this part of the image must generate the rest of this image here. So this method is weird. What they do is they basically reformulate the autoregressive training technique to make it much more like this this sequence generation here. And in fact, they basically need to add they basically want to formulate this in two ways. An autoregressive sequence needs two things. The first thing it needs is tokenization. Their claim is that this is a weird way to tokenize things, and we'll get into that in a sec. And the second thing is it needs to have a one-dimensional sequence. It needs to have some way to have this one-directional causality. This method here does not have either. It does not have a obvious tokenization that's good, nor does it have a one-dimensional sequence that is causal, or a good way of modeling that. This is kind of like a brute force way of doing that, or a weird way of doing it. So they reformulate it. So what do they do for tokenization? For tokenization, they say it would be better to take this image and basically extract the features and to tokenize it in that way, tokenize it feature-wise. They say that this method here, it basically destroys the structure. Let me reduce this down to a 4-pixel image, very large image, very high resolution. So if I have this 4-dimensional image, or this 4-pixel image, not 4-dimensional, if I have this 4-pixel image, you can see that everything is 1 pixel away from this pixel here. But if I flatten this into a vector, like so if I flatten it into a vector, like this, 1, 2, 3, and 4, then 1 and 2 remain 1 hop away, but 1 and 3 do not remain 1 hop away. That's 2 hops away, and 1 and 4 are now 3 parts away. So if you imagine each of these as patches, and this is our sequence here, this basically destroys the structure of the image. It also removes locality because the locality is just gone. The structure is gone. It's completely different now. So their claim is that patching is a bad way of modeling an image as a sequence of vectors. So what they do is they throw this through something called VQGAN, or I think it was initially VQVAE, and then you can add a GAN loss on top of that to make it VQGAN. Basically what this does is you have an image. So let me take this image up here. There. Come here, image. So if we have this image, you can send it through a variational autoencoder, which takes this image here, which is, say, L by W by 3 channels, or 4 if you want RGB, or RGBA. We'll just work with RGB. So you send it through this encoder, and the encoder is going to produce some latent form of the image, which extracts all the features, or hopefully extracts the features and compresses it down to some L, where L is much lower than L, and W, where W is much lower than the original width. So maybe you compress this from 512 to, say, 16. So 512 by 512 by 3 to 16 by 16 by C. So you're compressing this image into some feature representation of the image, into this latent space. You then send this through a decoder, and this decoder then blows the image back up. So we take this image here. After the latents are sent through the decoder, you hopefully get out a good reconstruction of the image. Maybe there's some noise in it, but it's hopefully a good reconstruction of this image here. Now, this is a continuous process. This is continuous in a way. This is continuous, and this is continuous. So all of this is essentially in a continuous space, or all this is in a continuous space. What you can do is you can add a quantization part right here. So I have drawn this out over here. And what the quantization part does, whoops, did not mean to do that. What the quantization part does is it essentially takes these vectors, so the C vectors, and it tokenizes it. And the way it tokenizes it, it basically converts it to a discrete sequence. So, and to do that, it uses a lookup table. And this lookup table basically has a bunch of features, and you basically do feature matching. So let me take our sequence here. This here. And what you do is you take each vector. So you take each feature vector. So you take this first feature vector here, which would be a C-dimensional vector, and you have your lookup table. This will be your quantization lookup table, and this is going to be a C by V lookup table. And you can think of this as basically your vocabulary. This is your vocabulary that you're going to use for your discrete transformer modeling. Think of this as the embedding process, where you take text and you embed it into this discrete representation. This is very similar to that. We're taking an image and we're embedding it into a discrete form the transformer can use. Just text is a lot easier to do that with intuitively. So we take this vector, and what we do is we look for the vector that is closest to that vector, using Euclidean distance. So we take this vector, we look at every vector in the codebook, and we find the vector that is the closest to this vector here. So you would then represent this as an integer, say 17 is vector 1. You then take this vector here, and you do the same thing. So maybe this is vector 37. And you take this vector here, and it is no longer 420. Yesterday was 420. However, we'll represent this as 420. There we go. And this is basically the sequence that you're creating. So you then end up, after you quantize this, you end up with an integer. So this is floating point, this is continuous. After quantizing, you end up with an integer for each of these feature vectors. So this would be 17, 37, 420, and so on. So this is your quantized discrete representation. You can then flatten this. So this is then flattened into a sequence here, a sequence of integers, 17, 37, 420, and so on, where this is going to be a L times W vector. And then you can turn this into the sequence by just taking the corresponding vectors here. So this would be vector 17, this would be vector 37, 420, and so on. And this is now your representation of the image. However, in this case up here, you would add a positional encoding saying this is position 1, this is position 2, this is position 3, so that it can autoregressively model that. In this case, we aren't going to do that. So the order doesn't matter. You can just as well take this vector, move this one up here, move this one up here, and as long as you reconstruct it properly, it's fine. The order doesn't matter because we're not adding positional encodings. So this is the quantization part. I have drawn it out over here, hopefully for more clarity, so you can see the entire process. What we do is we take an image. So we take this image, we then throw it through an encoder. The encoder gives you a feature representation. where the dimensionality is much smaller, and it is now in a feature representation where every feature is represented by a different channel. This also does mixing with all the image, so this part of the image here knows, or rather, this part of the image here probably knows about this part over here, but it also has local information. So it has local and global information of the image because the encoder mixes up the information in the image. So this is some feature representing the image. You then quantize this using your quantization codebook here, and this gives you codebook indices for your entire image. So this is what we're going to use to do the modeling. We're going to use this part here, and the modeling step is going to be right here. Now, assuming we have this image representation, we can then decode it by going to our lookup table. We can then get the vector representation for each part of for each quantized embedding, or for each quantized feature. So we get the corresponding embeddings from our lookup table, and then we decode using those embeddings. So the whole point of this is to take a continuous feature, to take a continuous image, transform it into a smaller dimensional feature space, and to use these as to use these to model the image, rather than using something else. So that's why we do this. Now we have this thing. We have this feature representation for our images in a discrete space. So how do we model this with the transformer now in a causal way? So remember that the second part is you need a one-dimensional sequence. So we have tokenization with our VQGAN. Now we need to make this into a one-dimensional sequence to model this causally. So the idea is here. Instead of modeling this, go up to this image here. Instead of modeling this so if we look at the text, or if we look at the paper, instead of modeling this where you model one patch, which then generates the next patch, and then this patch generates the next patch, and this one generates the next one, like I showed before, instead, we will model it in this way, where we have a super low resolution image. In this case, it's a 1x1. You can think of this as kind of the seed for a diffusion model. You can then upscale, you then have the transformer, the next generation, or the next step of the transformer will not be another part of the image, rather it will increase the resolution of the image. So this part here is so this will be time step equal to 1, and this will, or 0, and this will be time step equal to 1. So the next step, it does a whole generation process where it does a whole process where it generates the next resolution of the image. You then then the next step is to generate the next resolution of the image. So the resolution gets slightly better, and this is t is equal to 2. And then you do it again, resolution gets even better. And you keep doing this. So the process isn't over one image, the process isn't over an image and parts of the image. Rather, the process is over an increasing resolution of the image. And this is the causal part. This part over here is causal in that it depends on the rest of this part here. So the way you do inference is you will give it some random seed, and maybe you can guide it using conditional guidance, and it'll slowly increase the resolution of the image. Each step is an increase of the resolution. It's not a new patch generation of the image. This is the idea. And this defines our one-dimensional sequence. This is a one-dimensional sequence, and this has obvious direction. This is obviously causal. This depends on this, depends on this, depends on this. There's an obvious 1D causal direction, unlike this original this original image generation method where you generate one patch at a time. So they mention that there's multiple problems that this method addresses over here. The first is mathematical premise violation. So the problem is that the original method it's not really causal. Like, it basically requires bidirectional. Whenever you have an image encoder, it basically is bidirectional, so it encodes the whole image. And if it encodes the whole image, you can't easily do this generation here, the causal generation. However, here, since you're doing causal generation image by image rather than patch by patch, you can encode an entire image, and the bidirectionality doesn't matter because the bidirectionality isn't in the image, it's in the resolution, which isn't encoded in the encoder. The second part, which is probably more important, is the structural problem that I mentioned earlier, where patching it gives you this structure issue. The structure is lost. And the third is inefficiency. So if you do it using the normal causal method, it's very inefficient because it has to generate patch by patch, and that becomes problematic. However, they prove that instead of it being O of n to the 6, it is O of n to the 4. So it's better in that case. And those are the three things that they say this new method fixes. It also makes a lot more sense to generate in this method than the other method. So this is the whole paper. It's essentially you use a VK or a VQVAE or VQGAN to encode your image to a discrete representation. You then take the discrete representation and you decrease the resolution, and you use that to do inference causally. Let me show you real quick what this may look like. So if I have some image here, so image cat, bam, cat speedrun. So what we can do is we can create multiple resolutions of this. So let me use this as one resolution. Let me decrease the resolution a little bit, like that. And let me decrease the resolution again, like that. There we go. Now we send these through the VQVAE or VQGAN, and maybe for this first image, it generates one token, just for ease of me drawing one token. And the second one generates two tokens because it's slightly higher resolution, and then this one generates three. So the sequence that we're going to model causally, maybe I can draw this in blue, like this, and this can be in red. This will be our third, and this will be our higher resolution. So the sequence we're going to model causally is this sequence here. You have this representing the first image, this representing the second image, and this representing the third image. So we then throw this through a transformer, and this first token is going to predict so this first token is going to be some number, so 17. Now, what we want this token to predict are these two tokens here, instead of just one token, or instead of just modeling the next token here, it's going to model this whole image here. So that's what it's doing. And it'll make a prediction for these two tokens here. And then these two tokens here will make a prediction for this token over here, for these three tokens over here. And this will be the sequence that we're modeling. So this will be t is equal to 1, this will be t is equal to 2, and this will be t is equal to 3. And this is what the transformer is going to model. We can see that over here, where you have this first resolution here. The first resolution generates the second resolution, and the second resolution generates the third resolution, and so on. This is the causal behavior that we want, and this is how it's going to be modeled. They define exactly the losses they use down here. Maybe up here. Yeah, here we go. So they have this loss function here, and the loss function has 4 parts. Basically, this is just extra losses. You got your perceptual loss and your discriminative loss, making your latent nice and your image. This is just not pixel-wise. This is more feature-wise, and this is just your discriminative loss. You can slap on a discriminator, and it makes it better because it does. This was done in Stable Diffusion as well for the autoencoder. This one here. So if we have an image, the encoder maps it to F. So this is your features. This is your image in image space or pixel space, and this is your features in the latent space. So this is just latent matching, and this latent reconstruction, And this is used to train your quantization lookup table. And this image to image, or this image reconstruction loss, is used to train your encoder and decoder. So this is a loss. These are the losses, as you may expect. Yeah. So one thing they also, so apart from this whole thing, the one thing they also add is a residual method. So instead of modeling this completely where you go from one resolution and then you have to completely model the next resolution in the next step, and you have to model the entire image, they use a residual method where this first token here basically takes a guess at what the image is going to look like. But this part here does not represent the image for the second resolution. So it doesn't look like this up here. It doesn't look like this, where this is some image, this is the next image, this is the next image, and this is the next image. Rather, this is going to be the initial guess. This right here is going to model the residual of this. So basically, what is the error of R1? R3 is then going to model what is the error of R2, and R4 is going to model the error of basically the accumulation of all these. So every step is modeling the error at a higher resolution, and that's what they define down here. So they define this multi-scale VQGAN encoding. Rather than encoding something to just model an entire image, you encode it to model the residual. So we can look at that here. So what they do is they take the image and they first encode it into this feature space. So F is our features, and F is going to be our H by W by C. So H by W by C is our feature space. Then for every resolution, so from low resolution 1 to high resolution K, you then first interpolate the image, and basically this interpolation brings it from H by W to whatever the resolution is. So in when K is equal to 1, this would be 1 by 1, and so on. When K is equal to 2, maybe it's like 4 by 4 or something like that. So some increasing resolution where, and it just interpolates it down. So Q then quantizes it. So this converts it to integers, and RK is the integer representation. So this will be H by Q, or maybe I'll call it like L by W, A by B by 1. A by B is the new resolution, and 1 is the quantized integer form. You then throw this in the queue, because we're going to use this later to do decoding. And then what you do is, since we want to model the residual, this is basically going to be our first guess at basically the first representation of what this image looks like. So imagine you take this image and you're encoding it into one vector. There's going to be a lot of error. We want F to basically model that error. So what we do is we take the integer representation, we then throw it through the lookup table, and we get the embedding vectors. So we then convert this to A by B by, say, C again. So this is just taking this discretizes it, this is saving for later, and this takes the discretization and converts it to a token form. So we take the integer and we convert it to a token. We then, so they say interpolate here. Interpolate is used to downscale and upscale an image. So this upscales it to the original resolution here. So this is now L by W by C, the original resolution that was in the original image. And then what we do is we say, how far is our current image, so whatever the image is, or the feature space rather, so whatever our image looks like, and how far is our guess from that. And they also have phi here. The idea of phi is you take this, you throw it through phi, and it helps with the low resolution problem. But you essentially say, how far is my current representation of the image from the actual image itself? And then you use that for F. So the idea is, in the next step, so whenever K is equal to 2, we're modeling the error that we made in the first step. and then we then subtract that from the error, and then we have a little bit more error, and the third step will model that error. So as we increase the resolution, we're modeling the error that the past sequence made, rather than modeling the image at every step. We're modeling the error at every step. So first step generates the initial guess of the image, and then we model the error, rather than at every step we model the exact image representation. So we can decode this here by just iterating. So we start with zeros, and what we do is we iterate through the sequence, starting at k is equal to 1 and going to k is equal to k. So low resolution going to high resolution, and at the low resolution, we then take our guess. So this is our residual guess here that we pushed in the queue. And we take this guess. So this guess is going to be A by B by 1. We then send it through the lookup table. So this will be A by B by C. And then we interpolate it. So blow it up to the original size of the image. So this will be L by W by C. And then what we do is we basically are reversing this process. So instead of subtracting it, because we're not modeling the error, we're trying to reconstruct the image, we then just take the prediction and we add it to this. So we started with zeros, and in the first step, we're basically going to take the initial guess and turn it into our current reconstruction of the image. And then we do this again. We take the second residual, the second set of residuals, we look it up, we then interpolate it, or extrapolate, or blow it up to the original size, and then we add it to the original. So like I said, this models the error, not the exact image. And then at the end of all this, we should have an f hat that hopefully reconstructs the image. And then we can decode it, and hopefully it looks just like the image. Over here, kind of in a weird way, you can think of this first vector as kind of getting the structure, so maybe the face and all that. And then the second step is going to model, oh, maybe we can get the error is like, oh, there's some error here. There's some ears that are missing. Maybe it gets one whisker. But this is a little bit higher resolution that it's modeling, so it has a little more to work with. And then R3 is going to model the error of these two parts combined. So maybe it models like the mouth, some whiskers, maybe some background stuff. And hopefully, when everything is done, you can add these all together and you'll get your image that is reconstructed using this error modeling technique. So that's what they do. And this is similar to like residual vector quantization, which is usually used in audio, like in codec and stuff like that, rather than normal vector quantization. And it usually performs better. One thing in their code is they actually just use one codebook for this entire process. So they use one codebook at every resolution. That means that you have the same vocabulary at every resolution. I'm curious if a different vocabulary at each resolution would make it better, but I'm not sure. So this is the entire process. Encode an image to some latent space. Quantize the image. You then do training in this quantization part. So similar to how latent diffusion works. So you do it in this part. And then you can reconstruct the image by dequantizing it. So you basically throw it through the lookup table, and then you can decode the dequantized states to get your original image. And that's all that's being done. Where this part here is trained by an AutoRegressive, or this part here is modeled by an AutoRegressive technique, where the resolution is the 1D sequence rather than the image patches. So this is the model. This is what's being modeled. Now, the results are really, really good. So one thing they show is that DiTs, diffusion transformers, do not have the scaling properties that normal transformers have. If you increase the size, the FID doesn't go down linearly, though with their model it does. And they have a bunch of proofs, or they have a bunch of empirical work that they showing that this is linear to some high degree. I think it was, where is it? It's basically -1. So they show that this has the desired scaling properties that we see in transformers. but DIT does not. So that's very nice. That means scale is all you need like normal. They also show that it has really good results. If we go here, yes, so it basically beats it beats a diffusion model in terms. So this is ImageNet 512 by 512, and on conditional generation, it beats ImageNet, and it beats diffusion models, which take a really long time to generate. And diffusion models are the go-to method right now. It beats them in terms of FID and inception score, and it's way faster to do the generation because you're not doing this diffusion process, you're doing this upscaling process. They also show that it has really good results compared to every other method. So you have GAN, you have diffusion, you have autoencoder. What is this? I think this is AutoRegressive. I'm not sure what this is. And then their method. And they show that it is way better, but it's also way faster, while autoregressive methods are bad and slow. So normal autoregressive. So this model, it's really has really good results, and I am very curious to see how well it does in practice, because it looks really good. They also have linear scaling laws, and then they have some samples down here which look. That's a bird. That's definitely. Oh, I don't know if that's a dog. That's a dog, hopefully. Yeah, they have some more stuff if you're curious, and then they have the proofs as well for scaling laws. Or for the time complexity. So yeah, they have all that, but this method is very cool, and I'm very curious to see how well it actually performs.